All right, everyone. So good morning. Thank you all for joining us. So today our speaker is Mark Giovinazzi, who will be presenting a reanalysis of the KELT-24 exoplanet system, host to the hot Jupiter KELT-24b, and as it turns out, maybe some other stuff too. So Mark is an NSF Graduate Research Fellow at the University of Pennsylvania, where he will be defending his thesis this spring. Thanks, Joe. His research focuses on low-mass stars, binary systems, and the detection and characterization of exoplanets, primarily through the use of radial velocities in astrometry. Mark's also a member of the NUID science team and is active in the extreme precision radial velocity community. And so with that, I will yield the floor. Please take it away, Mark.
Awesome. Great. Thank you so much, Kellen, for that great introduction. Thank you all for being here today. My name is Mark Giovinazzi. I'm a PhD candidate at the University of Pennsylvania. And today I'm going to be talking about a project that I've been working on the past year that depicts a cautionary tale of our interpretation of a nearby exoplanet system. And in this work, I'll describe the trials and tribulations in the reanalysis of a really curious exoplanet, KELT-24b. And I'll talk about, as you'll see, KELT-24b is a very complex exoplanet, and the history of it is multi-layered. But I'll show why this is a great example of why we need more dedicated efforts for stellar and planetary modeling. But first, I want to make sure I set the stage by filling up everybody's bingo cards and begin by building from the ground up to tell you about some of the ways that we are currently discovering and characterizing and modeling all of the many worlds that we currently know of beyond our solar system. So the radial velocity method is one of the oldest exoplanet detection techniques that we use. It was the primary way that we found our first exoplanet, 51 Pegasi b. And the way that this works is we are taking spectra of a star over time. As that spectra shifts back and forth, it may be indicative of, in some cases, orbiting companions like planets as you see here. This is oftentimes used in conjunction with the transit method that is monitoring the brightness of a star over time. As you can see in this cartoon, as the planet crosses in front of the star, we notice a small dip in the stellar brightness, and from this dip, we can back out many important physical characteristics of the planets that are orbiting them. Now, primarily of all the planets that we know here, more than 3/4 of them are known to transit. And so the way that we choose to model our exoplanet systems that are known to transit is very important. Just to highlight a few things, of course, a lot of these transits are on very short periods. This is an observational bias, but we can only really study the exoplanets that we currently are aware of. And so given this bias, even so, how we model our transiting planets is really important. We want to make sure we're understanding them correctly for the future of exoplanet discovery. So for about as old as the exoplanet community is, maybe going on 30 plus years now, at least in terms of the first exoplanet discoveries, there's an age-old saying that goes that you only know your planet as well as you understand the properties of your host star. Know thy star, know thy planet, etched into stone many, many, many years ago. And we still follow by it today, and it's a very important lesson, one that KELT-24b is a great example of. Now, the general template for how we model a star, and then therefore the planet, is to begin by taking spectral energy distributions of some array of broadband photometry, combining that with an evolutionary track, and some transit data that you have from your exoplanet. And from each of these three different sets of data, you can extract information about the stellar temperature, the luminosity, radius. The transits directly inform a constraint on the stellar density. And what you want to do is, as a recipe here, you want to mix that all up, and you can kind of cook up a solution for your stellar parameter set. And then if you're like me, you love to just season a little bit of radial velocities on that too, to get out some information about your planet, the mass, the orbital properties. And as a member of the NUID team and a very dedicated radial velocity fan, I can never have too many radial velocities for my planet. So I always love to make sure I get a lot of those. But this is a general template that we use to solve for exoplanet models. But for the case of KELT-24b, I'm going to talk about why this template, though it seems sort of well-contained and you get all the information you need, we need to be more dedicated in the investigations that we use for solving for some of these stellar properties and how we use those to infer the properties of our planet. So I'm going to go back and give a little bit of a history lesson on this system Because back in 2019, here's a screenshot of 2 astro pH submissions just 5 days apart. The top panel here by Rodriguez et al. Published a system called KELT-24b, and this is a hot Jupiter orbiting a nearby bright star. Well, just 5 days later, some group led by Horth et al. 2019, they published a very similar looking paper, also finding a hot Jupiter, also around the same star, and they effectively found the same planet, independent of each other, an independent discovery of a planet orbiting a star previously known as HD 93148. Here we adopt the language KELT-24 just because that is the nomenclature that the NASA Exoplanet Archive chooses. And so hereafter we will dub this star and planet KELT-24 and KELT-24b. So while they found the same planet, maybe there's some just coincidence about that. They did happen to find a lot of very similar properties about it. This is a hot Jupiter. We knew that much. It was a very bright star in a young system about 100 parsecs away. The hot Jupiter had a period of about 5.5 days, and it was near super Jupiter mass at about 5 Jupiter masses. And both agreed that the system was relatively well aligned, and I'll explain a little bit about that, what it means later. And also that it was on a notably non-circular, but also not highly eccentric orbit, and this sort of lends itself towards a lot of very dynamically interesting questions that we can explore as well. And here I'm just jumping a little bit ahead by showing a snippet of a test light curve that we have on this transiting exoplanet system, where you can see that the planet, or at least the data we receive from the planet, is very well behaved and well described as a repeating transiting exoplanet. So there are just 3 very clean transits that we get here, about a 0.9% transit depth. However, though they both agree there's some big Jupiter orbiting very close to this hot star that's nearby, and that's interesting for a number of its own reasons, when you look closely between these 2 concurrent publications, they identified highly discrepant values for their stellar properties. So if you take a look at the stellar mass in the top panel, you can see that Horth et al. In the orange identified a stellar mass of 1.3 solar masses, whereas Rodriguez et al. Found a stellar mass much higher at about 1.45 solar masses. And maybe while the point estimates of these 2 values don't disagree by that much, they're well beyond the derived standard deviations of both of these estimates. And so that's slightly concerning, and it raises some red flags. But we find these discrepancies all across the board in terms of the physical properties of the system. If you look down to the stellar density, just 3 panels down, again, there's a difference there in how those 2 were derived. And the ages as well of the system varies quite drastically. Horth et al. In fact found the age to be a lot closer to 3 gigayears as opposed to Rodriguez et al. 1 gigayear. And know thy star, know thy planet. So the derivation that we have for our stellar properties are, of course, going to inform those of the planet. And so no surprise, we find, again, a pretty statistically significant different version of the planet in each case. Sure, they're both big Jupiter-sized planets, but if we look at the mass of the 2 planets that each derived at the same time, one finds 4.2 Jupiter masses, one finds 5.2 Jupiter masses. These are 2 different planets that they're solving for. These are not the same thing. The planet density differs a bit. This offers a lot of different, this changes the conversation a little bit for what type of planet we're actually finding. And so coming back to resolve this is a pretty important scientific question. But just to set the groundwork a little bit for how both of these solve for their planet and their star, both of them use transit photometry. As you can see on the left, we have Rodriguez et al. That used about 30 transits from the kilodegree extremely little telescope, and you can see a phase-folded light curve there. And then on the right, we have the Horth et al. Paper, which used Mascara, the multi-all-site camera array that got about 20 transits from there. And you can see both of them find a well-behaved transiting exoplanet. And those are basically all the photometry that was used for both of those data sets. Notice there's no overlapping data here between the 2 publications. And then in terms of radio velocities to help pull out and extract the mass, Rodriguez et al. Used 96 spectra from 2 separate instruments, Minerva and Trace, whereas Horth et al. Used 110 radio velocities from SONG, the Stellar Observations Network Group. And again, you can see in both cases we have the phase-folded radio velocity diagrams, where you can see that they're both picking out a periodic signal that matches the 5.5-day period we see in the transit. And both are just whopping signals. If we pay attention to the semi-amplitudes here, these are about a 500 to 600 meter per second semi-amplitude. So it's a giant signal here that both were very easily able to pull out. But another thing that we can do when we have radial velocities and transits, or radial velocities of a transiting exoplanet, and this is something that both groups did, is they took advantage of the Rossiter-McLaughlin effect, or the RM effect, which is a measurement you can make on a transiting exoplanet to determine its relative spin-orbit angle, or its relative alignment with respect to the spin-orbit axis of the star. And as you can see in this diagram here, as a transiting exoplanet moves from ingress to egress, it's going to block out different portions of the light that is being emitted from its rotating star. And as the star rotates, half of that is going to be moving away from you and blue shifting, or red shifting rather, and half that is going to be moving closer towards you, and that will be blue shifting. And so blocking out some of the bluer light gives you a relative RV bump in the radial velocities you'll measure, and just the opposite of that for the red. And so what this does is it allows us to extract a spin orbit angle, or lambda, as I denote here in the diagram, where this angle tells you about the orientation of the planet's planar orbit with respect to that spin axis of the star. And understanding the spin orbit angle of these stars, or these planets rather, can teach us about the alignment, and then therefore we can make some inferences about what the evolutionary history for some of these systems can be, which is notable for cases of hot Jupiters like KELT-24b, because we don't often expect these types of planets to emerge very close into their planets. And so these angles can tell us about whether the movement towards that inner planet that it is was more chaotic or maybe more gradual and smooth. So both of these analyses, Rodriguez et al. And Horth et al., were both able to take advantage of this fact and make radial velocity measurements during the transit. Now, on the left here, Rodriguez et al. Did a very similar measurement, a very similar thing to making that RM measurement by using Doppler tomographic measurements, and this is effectively a radial velocity, or rather, this is using the RM effect in spectrospace. So rather than taking high cadence radial velocities during the transiting event, they actually did not reduce the spectra, and they just did this in two-dimensional space, where you can see in the left plot, we have a Doppler tomographic measurement of a bunch of in-transit versus out-of-transit spectra. And you can see from left to right in the center, we have this what's known as a Doppler shadow that transits across that spectra, which you can use to extract the spin-orbit alignment. And this is exactly similar to the type of measurement we use in the RM effect. It's just in this spectra space rather than using the derived RVs. And then Horth et al. Use high cadence radial velocities in transit that more directly mimics the effect I just described, and also found an alignment of the inner planet here, KELT-24b, to be about edge on, or 0 degrees. Both of these, unlike some of the physical properties we found in the star and the planet, are relatively consistent with each other, which is a good check. So to resolve some of these, or rather resolve, I should say, some of these discrepancies or inconsistencies that we had from the original two publications back in 2019, our first approach here was really just to hammer away at this system with data. Let's throw on a bunch of new radial velocities, let's try and get some extra photometry, and let's see what we can't get to the bottom of here. So our first step was to go to Minerva, which is the miniature exoplanet radial velocity array that sits atop Mount Hopkins in Arizona. It's an array of 4 telescopes where those back 4, 1, 2, 3, and 4 from left to right. The front one is a separate telescope associated loosely with the Minerva collaboration. But these 4 telescopes all collect spectra independent of each other, and for fitting purposes are treated as different instruments too. But we went there and we collected 201 new radial velocity measurements between 2019 and 2020. And as I was putting this together, I actually happened to realize that I was on Mount Hopkins at Minerva kind of serendipitously during the early collection of these radial velocities. So I find maybe it was destiny calling for me being there during the early collection of these radial velocities to one day I could be the one to come back and solve this long-standing disagreement between the two publications. So that's me in front of the telescopes. I did not collect any of those radial velocity measurements, and it's a good thing because I probably would have messed it up. But this is a this is a robotic array too, so thankfully there's no hands-on observing needed for those. Another thing we're able to do on top of those 200 radial velocity measurements, which nearly double the RV data set that we had on the system, we were able to use 36 new full transits from TESS across 8 sectors, as you can see in the diagram here, And this is great news because previously this system had no test observations just because the two publications predated the sector where tests began to observe KELT-24. And so this photometry, as you can imagine, is very valuable to be able to help maybe constrain and rule out some of the possible sources for discrepancies between these two original publications. In sector 40, though, we found something very curious, which was this deep single transit that is found nowhere else in the baseline of tests. And it was observed on July 19th, 2021. You can see it has a transit depth of about 0.6%, a duration of about 12 hours. You can see it there sort of interspersed between a few of the KELT-24b transits, which we do expect and see across the test baseline. But this depth could be, or this transit rather, could be a longer outer planet, something else kind of going on. It's a very integral part of the rest of this analysis, and one that we're not actually sure, spoiler alert, what it actually could be. But we tried to figure it out anyway, and we did some brief analysis, just given the fact that tests observed for a few years now, and the fact that we don't see it, but we only see it in that one place, what types of periods could be allowed where the other transits would have fallen at a time when tests wasn't observing. And what we find is something a little bit unsatisfying in that we can't rule out a lot of space. It's not some short period thing as you would expect. So all the green area here are the allowed regions in period space of what type of orbiting body, assuming it's periodic, could possibly be the source of this transit. So anything in the neighborhood of order hundreds of days, or of course beyond the baseline of tests at around 3 years, you just can't really rule out. But we did kind of give a quick stab at seeing what sort of space we could rule out here. Now, in 2019, when Rodriguez et al. Published their discovery paper, they identified a nearby, what they call the background source to KELT-24. So you can see in the bottom left plot here, KELT-24 is the brighter of these two stars. They went after with an image using a BR gamma bandpass, and you see on the bottom there, circled in black, is this background source that they tried to model the flux out for, just to consider that effect photometrically. And what's noteworthy is that these two sources being only 2 arc seconds away from each other, they're close enough that they're actually in the same pixel. And so theoretically, if a transit were to have happened behind that star, which you can see on the right, does contribute 10% to 1% the amount of flux as KELT-24, a transit of that background source could theoretically have been caught by tests as the single transit. And we also note that Gaia measures this background source to have a renormalized unit weight error, or RUI, of 1.81, where the RUI metric by Gaia is effectively a statistical measure of the goodness of fit to a single star solution. And the baseline here of what is considered as a good single star solution is anything below 1.4. So being 1.81, this is generally thought to be an unresolved binary, some sort of a stellar multiple, some kind of a giant planet that's causing astrometric movement of the star that is causing it to jiggle a little bit and not appear like a single star. Another possible source for a high renormalized unit weight error is blending from nearby bright sources. However, in the case here, 2 arc seconds away is actually just sort of beyond the limits of what you would expect, or where you would expect blending from a nearby bright source to actually come into play. So we do believe this 1.81 to be sort of physical, at least isolated to what we understand about that background source. We don't expect it to be blending from the brighter KELT-24. But El-Badri et al. 2021 identified these two sources as actually likely bound, given consistent parallaxes and that they were co-moving. And we did some additional analysis too, using some instantaneous proper motion measurements from Gaia and some other small analysis to estimate an orbital period of about 3,000 years, and also find that these two sources are likely bound. And so the fact that this is not only contributing a flux that is about 10 to 1%, as you can see in the SED here, the fact that it is bound makes it an interesting player here in this system, and certainly as a possible source for that apparent eclipse. So to dig into this a little bit further, we were able to process an already existing AO image that was just sort of sitting on the Keck archive unpublished and unprocessed, using NERC2, which was taken, actually I think June 10, 2019 was smack dab in the middle of when the 2 papers were published. One was June 7th, one was June 12th. So there's a little irony in that too, that this was taken back then. And as you can see here, we have KELT-24, which is masked out a bit, and then we have KELT-24b, which you can see down and to the right. And we got this epoch of imaging utilized 3 imaging modes. So standard imaging, which allowed us to extract some relative astrometry of the 2 stars. Coronagraphic imaging, which allowed us to place some contrast limits on both of these to search for other nearby sources. And we also were able to use some non-redundant masking, which was great for achieving high angular resolution between both of these sources here. And what was also great about being able to resolve both of these sources in this NERC2 K prime band was that we now had 2 epochs of resolved photometry of both of these sources in the Gaia G band and in the NERC2 K prime band that we just processed. And most other sources, like 2MASS, for example, observe the star. It blends both of those stars together. And so all of a majority rather of the broadband photometry we have are not actually magnitudes of KELT-24, but rather composite magnitudes of these 2 sources. And so by having this resolved photometry here, we're able to do a little bit more analysis to try to back out some interesting qualities here. So I bring up 2MASS primarily because what we notice is that the NERC2 K prime band, it overlaps in terms of the filter, the transmission filter here with 2MASS's K short band almost identically. And so we made a small assumption here that the apparent magnitude we would measure from the K prime band could be approximated to be that we would see from the 2MASS K short band if it could indeed resolve both sources. And so by having a 2MASS KS composite magnitude as well as this delta KP magnitude from our newly processed AO image, we were able to go ahead and actually place these 2 sources on an HR diagram. And we also throw in there as a black line the missed evolutionary track for a 1 gigayear solar-like star with a metallicity of 0.2, similar to what we find for KELT-24. And what we see is that the primary KELT-24, denoted as the yellow star A in the top left, is well described as a single star that is along the main sequence track, whereas this nearby bound source, denoted here as KELT-24b, actually appears to be quite overluminous for its color. So while this could be a really unusually faint M-type star, it's actually a lot better modeled as an unresolved binary that is really just 2 M stars masking as 1 overluminous star. And this comes back to the fact that we know Gaia observed this to possibly be an unresolved binary, things like that. So things are starting to fall into place a little bit, where this B source here seems to be more complicated than how Rodriguez et al. First identified it as just some background source contributing a little bit of extra flux. We're also even further able to do a bit of a centroid analysis where we computed a difference image centroid that notably favored KELT-24b as being the actual source of the single transit. So we searched all the background sources in the test pixel and were able to find that none of them were good fits whatsoever to being the host of the single transit, but that it could be either KELT-24 or KELT-24b, while the overall likelihood between the two was, or the likelihood difference rather, was quite small in terms of whether it was KELT-24 or KELT-24b as the source. The analysis did slightly prefer KELT-24b as being the source of the single transit. And this would be really interesting because what it would suggest is that we have an eclipsing binary in KELT-24b that is actually bound to a transiting hot Jupiter system. And so what we've got are these 2 edge-on cases that, based on some rudimentary orbital analysis we've done based on some instantaneous Gaia proper motion measurements, among a few other assumptions, we can estimate an inclination that is pretty off edge-on. And so the idea is that if these 2 stars, or these 2 systems here are orbiting edge-on, but they themselves are not edge-on, architecturally it's a very curious system and one that poses a lot of really interesting questions about how this could have come to be. And so this is really interesting to us too. So this is sort of currently our best belief of what this picture might look like for these 2 stars. So what started as a nearby contaminating source that Rodriguez et al. Modeled in their SED, we thought that's not really quite right. Actually, it's probably a bound companion. But it's not actually just bound, it's more complicated than that because it's an unresolved binary. So it's some bound, unresolved binary, But then we realized it's probably more complicated than that, and it in fact is some bound, unresolved, maybe eclipsing binary companion, possibly, that we denote hereafter, maybe KELT-24 B/C, where B and C represent the two names of those stars that could be causing it could also be an unresolved triple. I mean, there could be a lot of things going on underneath the light that we're able to extract from here. But what we do know is that this source is overluminous when we treat it as a single star. And it's also a poor fit to a single star solution in Gaia, also suggested that it could be an unresolved multiple. And our centroid analysis, while relatively weak in terms of quality, it does actually prefer KELT-24b as being the source of these single transits. By being so close to KELT-24, it's hard to use that type of analysis to actually say for sure which one the source or the transit would have come from. But it is just sort of another domino here in just pointing to the idea that KELT-24 could not only be the source of that transit, but also be an eclipsing binary itself. We also did, in the analyses that I'll describe just after this, we considered a 3-star fit where we tried to go one step further than the analysis Rodriguez et al. Did, and consider the fact that both of these, or this bound source was actually 2 stars. But since we don't have any resolved photometry of that, it sort of introduced way too many degeneracies that really forbid reasonable convergence in our MCMC. And so for the remainder of this analysis, we do treat it as one source as far as at least the fitting routine goes, even though we acknowledge here that it's probably the most likely scenario that this bound source is in fact 2 stars. And so here is our updated SED that considers the 2 new adaptive optics imaging we have in the K prime band, which are circled in red here. And you can just see we have a pretty good fit. Everything's mostly in agreement with the broadband photometry we use. We use the 3 2-mass band passes. We use the Gaia G band, those 2 NERC2 KP bands, and we use the 4 band passes from WISE. So altogether, we have 315 radial velocities that we threw at this system, 200 new ones from Minerva, and an additional observation we got from TRACE to try and isolate one of these stars. But unfortunately, the fiber on these instruments are too wide to actually be able to resolve these 2 instruments spectroscopically as well. We also used 24 in-transit radial velocities from some previous work to help constrain the spin-orbit alignment. We introduced 36 new transits from TESS and 45 in total, where 9 of them come from the KELT follow-up network, which is this team of telescopes that went after a lot of KELT stars with transiting planets just to collect additional photometry on them. And we also include 11 broadband photometric points, 2 of which being those 2 from the NERC2 K prime band that I mentioned. Now, at this point, it's important that we highlight the 2 different ways that both of these papers modeled their stars, and then we can get into how we chose to model our system based on these discrepancies. It's something that we want to be really careful about, and it's the crux of this analysis, were the choices we made and how we modeled our stars. So starting with Rodriguez et al. 2019, they globally modeled their system, jointly fitting everything at once, including this now bound source. So they used a 2-source SED. They modeled their transits, radial velocities, and broadband photometry and evolutionary facts, imposing agreement all at once, whereas Horth et al. 2019 chose to derive their stellar properties strictly from the SED and the MISS evolutionary tracks and did not consider the bound source KELT-24b. And then they fixed their stellar parameters based on the SED and the evolutionary track, and then used the transits and radial velocities and all of those observables to actually solve for KELT-24b. Now, both of these, in theory, should work because while Horth et al. Did not use the transits for deriving their stellar parameters, this is an assumption that should be okay if you assume the fact that your transit-derived stellar parameters should agree with those from your SED, which in principle, both data sets should be good. So what we tried to do here is our approach was to present, which is something a little bit unique. You know, normally when you write these papers up, you present a final analysis, you've got one set of solutions, and you say, here's the right answer. Well, we're saying we actually don't know what the right answer is. So we're just going to present 3 different ways of trying to solve this by doing one method called global modeling, where we reproduce the fit that Rodriguez et al. Did. So we jointly do everything. We do a piecewise modeling that reproduces the method used from Horth et al. 2019, and we introduce this new assumption that excludes the broadband photometry completely and enforces a spectroscopic prior on the effective stellar temperature in order to counteract that fact. In each of these fits, we do include some spurious in-transit radial velocities that we get to help constrain that relative alignment that we see in KELT-24b. And we also do, so TESS's photometry automatically deblends any individual tick star based on some of the background that they measure. And so what we did is, since we had this new photometry on the two sources, most times the TESS deblending is quite good as a first pass. But since we had these resolved photometry and TESS did not resolve the two sources, we decided to undo the TESS deblending, and then we re-deblended based on our new photometry. So it's a bit of a complicated process, but we were very diligent in how we did that, and we believe that this gives us the best measure of the photometry that we actually have here. A bit more nuts and bolts just about these analyses. We didn't do anything too crazy in terms of our priors. We just enforced some Gaussian priors on our parallax from Gaia, our metallicity, our rotation velocity, as well as some uniform priors on the time of inferior conjunction that actually takes advantage of the long baseline of photometry we have from the original KELT survey. Otherwise, none of the KELT photometry was used. And then we have a uniform prior on the reddening here, where we effectively just place an upper bound on what it could be based on some galactic dust maps. And in red here, I'm just highlighting that this is a prior that we use only for the case where we exclude the broadband photometry from the SED. And this is enforcing a, without the SED, you have no really prior inference on what the effective stellar temperature could be. And so we derive this spectroscopically, in this case, from some trace spectra and use that rather than the SED. In each case, we assume that these two stars are bound, and as such, we just say that they have a fixed age, they're part of the same system, they have fixed initial metallicities, reddenings, and of course distances, and this decreases the degeneracy significantly, but we do believe that this is a safe and reasonable assumption given some of the co-moving findings that we have from Gaia for these two stars. So to summarize, what we're going to do here is this global modeling, we're going to jointly use all available data. So we've got all of our broadband photometry. For the global modeling, we're going to jointly fit all of the transits, all of the radial velocities, the SED, the evolutionary track. For the piecewise modeling, we're going to use our now two-source SED. So previously, Horth et al. Did not account for that background source. So that could have been some sort of a problem. So we throw the two-source SED in, and we consider the missed evolutionary track to solve for the stellar parameters, and then we fix those results just as they did, and then use the transits and radial velocities just to solve for the planet. And then our no SED case, which is the new assumption that we're presenting here, we exclude the broadband photometry and use only the missed evolutionary track, the transits, and the RVs, and that spectroscopic effective temperature prior to solve for all of our physical properties of the star and the planet jointly. So it's sort of a joint fit, just as in the global modeling, but now we are not using the SED whatsoever. So what does all of this look like? Well, first we can start at sort of the highest level and just look at how these transits all look. So by adding in all these transits, the 3x3 grid up top are the 9 transits we have from the KELT follow-up network, or KELT Fun. And these are older transits that were published in Rodriguez et al., but we do include those. And then here on the bottom, this is just a great figure of the TESS photometry, which really shows you the power and the precision that TESS offers in terms of observing some of these stars. And you can see we get a really great fit to this model here, and to this data rather. And so the TESS photometry turned out to be really, really clean for the star, and we believe that it helps to enhance the fidelity that we have in understanding the system. Now here's the phase-folded radial velocity we curve. Again, just some giant whopping signal that we've got. The semi-amplitude here we see is relatively consistent with what we found previously at about 500 meters per second. So it's a massive signal that we have now across 6 different instruments. The 315 radial velocities that we use here are all included. And subtracting that giant signal out, we see the residuals are mostly consistent with 0, which is a good sign. We then ran a couple of RV periodograms just using the simple Lohm-Scargo method. And before doing any sort of modeling out of a signal, we just fit a periodogram to the raw radial velocities. And of course, no surprise, we see some giant signal at about 5.5 days. That's KELT-24b. We also see an alias near about a day here that is, again, just an alias of KELT-24b signal. When we subtract out the best fit model, on the bottom here, you're seeing Basically nothing. A false alarm probability of 10% is shown there at the bottom, but the fact that nothing jumps out standing above that level kind of shows us that there's no other crazy signal here in the radial velocities that we're missing. Talk about the parameter space that we're maybe not sensitive to in terms of this system. What we've got here is a grid of minimum masses versus semi-major axes where all the colors represent untouched parameter space or unexplored parameter space that we can't reach due to the precision of our radial velocities. And so KELT-24 is a very active star. The typical RV precision that we can achieve is about 50 to 100 meters per second, which as somebody in the EPRV community makes me like really uncomfortable to say. That's like such a huge signal, but the star is so active, and so it's hard to get much better precision than that. So we make a relatively loose cut saying that any sort of signal that has a semi-amplitude less than 100 meters per second, we can't really make any assumptions about or try to fit for. So you can see there's Jupiter there shown for just as an example point there. There's a lot of space here where smaller amplitude, longer period signals could exist that our current analysis will not be sensitive to. The black space there up top is all of the space that we are, can safely rule out, but there's a ton that could exist under all this noise in our data. We're able to adjust or increase the confidence really of our relative alignment that the two groups had found earlier in their original publications. And so here we update the spin orbit alignment to about 1.5 degrees, plus or minus 5, which are smaller error bars than either group reported before. So this is nice. Not only do we find a good agreement that the star and the planet are well aligned, but we're able to, higher fidelity, agree that this planet is really, really close to edge on, which is quite interesting. So now kind of the meat and potatoes of this analysis, where we're going to present the results of those 3 different fits and also compare them to how they compare them to the original discovery papers too. So we can start with the star. What we're going to show is the blue, which is the same point used before for the Rodriguez et al. Paper. We have the orange, which is our piecewise modeling that follows the routine presented by Horth et al. And we have in green this no SED case that we use. And so for the stellar parameters, kind of surprisingly, we don't find agreement between these 3 models, which is pretty unsatisfying in a way. The stellar masses happen to agree relatively within a sigma, but when we look at the radii and compare them, we notice pretty statistically significant discrepancies here. So to highlight, take the blue color, for example, for the global modeling. This represented the fit we did following Rodriguez et al. The faded point here shows the original discovery paper's best fit, so that you can compare the faded orange there and the dark orange to compare the Horth et al. Publication, the dark blue and the light blue to compare the Rodriguez et al. Publication to our new fit. But we're still seeing, namely in the stellar density and the stellar radius, a lot of disagreement between these 3 models that in theory should all work and they all consider the same amount of data. So this is a little bit alarming and quite a red flag. And we can propagate these through into the planet and see something kind of similar. There is a little bit of convergence of what the best fit planetary mass could be, but unsurprisingly, disagreement in the stellar radius is going to lead to a disagreement in the planetary radius, and kind of all over the board in terms of what this could be, whether it's a 1.1 Jupiter radius planet or a 1.3 Jupiter radius planet. The fact that we have all this test photometry and we're this uncertain in what our radius could be is a little bit concerning. What is nice, though, in the bottom right panel, we compare the eccentricities of each of these best fit models, and we do find that all the radial velocities that we add to the system do kind of beat down the eccentricity to be closer to 0. And this is good because we, I mean, the data just are what they are, and the system is doing what it is doing. But we sort of expect for hot Jupiters like this, we expect to find them on circular or near circular orbits just because of tidal migration, and they may have circularized just being so close to their star. But there are oftentimes observational biases like the Lucy-Sweeney bias, where if you have a short baseline of radial velocities, even if your planet is perfectly circular, having not a lot of radial velocities can induce this effect where you appear to extract an eccentricity that is non-zero, when in reality the system is in fact 0. So the fact that adding more radial velocities brings this eccentricity down, as you can see compared to those faded orange and blue points, is sort of a good sign, and we do agree here about the planet's eccentricity. But to bring everybody's attention just to the stellar density, which is sort of really the root cause of where a lot of this discrepancy is going to come from, how we measure our stellar density, everything is sort of built on top of that in a way. And so when we compare the 3 different models using all the data that we get, just to remind everybody, in the blue we have a joint fit where the SED is considered with the transits to derive the stellar parameters, and in the orange we have a routine that uses the SED to derive the stellar density, fixes that, and uses the transits to derive the planet. And so by comparing those two, we have this direct disagreement between what the SED is finding for the stellar density and what the transit is finding for the stellar density. And the no SED, of course, here not use the SED and only uses the transits to derive the stellar density. So when we flash up the stellar density that we get when we only consider transits, just as an independent analysis, we find that unsurprisingly it agrees very well with the no SED model, just showing that the transit-derived density is highly discrepant from what we get from the SED. So something about the SED and the transit are inherently off, and there's a lot of cause for concern about that. So of course, the SED and the transit-derived are in disagreement. And one thing to note here is that I want to go back to the tests undeblending and the re-deblending. This is something we're really careful about, and so we sort of don't have much reason to, I mean, in theory, all of these different methods should be right, but specifically, we don't have any reason to think that the transits could be wrong in some sense. We believe those to be very accurate, where there are some assumptions you make in the calibrations that are made for your broadband photometry. We don't have broadband photometry for both sources, so it's possible something could be corrupted under the hood for modeling the photometry of that bound source KELT-24b. And this is sort of, to us, further evidence that the SED is somehow the source of error. We don't know how, but based on these observations, it's pointing towards something going on in the SED. Why does anybody actually really care about this? I mean, it's off, but you know, why is it so important that we get KELT-24b correct? Why do we want to solve the system? Well, primarily, it's a really great target for atmospheric follow-up. And just as a reminder, the way that we do this is you have planets that are transiting across their stars, and some of that starlight is going to trickle through the atmosphere of the planet, imprinting in its spectra important information about the planet's atmosphere. And so as a level 0 kind of way of what are the best planets for going after, you want the planets that have the most flux coming through their atmospheres. And KELT-24b, as you can see, we plot up actually the estimated photometric flux through the atmosphere of each one of these best fit models for the atmosphere of KELT-24. You can see it doesn't really matter. It's you know, which model we choose to use here. The point is that KELT-24b, regardless, is an excellent candidate just in terms of how much flux it gets through its atmosphere. Again, it's orbiting a really bright star. It's relatively nearby, and so it's sort of in the 90th percentile in terms of how many other exoplanets are receiving more flux than it. So this is a great cause for you know, KELT-24b being a good candidate for follow-up. But additionally, Kempton et al. 2018 produced this metric for measuring which stars are the best, most likely to receive the highest amount of SNR from JWST transmission spectrum, and they called this the transmission spectroscopy metric, or the TSM. And KELT-24b has among the highest TSM for all dense giant planets. And what we can do here is, if we just consider giant planets that have over a Jupiter mass and densities greater than 2 grams per centimeter cubed, we see that KELT-24 is right there at the top of dense giant planets in terms of the TSM. Depends on which model you choose to adopt. We kind of think the SED is the most likely source of error here, so we kind of prefer that no SED model, which does put it behind WASP-10b. But nevertheless, KELT-24b offers us a unique opportunity to be able to study how high surface gravity dense planets can affect their atmospheres. And just to bring some of this home a little bit further, we can highlight how dense and how high of a surface gravity KELT-24b does have. And again, here you can see in the blue, green, and the orange, the 3 different models we have for the stellar density, or rather planet density and planet surface gravity that we have compared to the landscape of all other known exoplanets. And you can sort of see that in terms of the insolation flux that KELT-24b receives, again, the models are discrepant, you know, sort of among themselves, but overall, we still see that KELT-24b, regardless of what the true answer here is, going to receive a ton of insolation flux It's got a super high surface gravity. It's a very dense planet, which is interesting for a hot Jupiter. And there are a few planets, particularly there on the top plot where we're comparing the surface gravity, a few planets that receive as much insolation flux that are as high of surface gravity as KELT-24b. And we also simulated a transmission spectrum just to sort of convince ourselves that this could be a good and viable target for JWST to observe. And so what we did here is we used exotransmit from Kempton et al. 2017. And by assuming a cloud-free solar metallicity atmosphere, something we believe is very well in agreement to what we believe KELT-24, the star, to be, we show that we're able to constrain abundances on water, methane, carbon dioxide, carbon monoxide, and we also believe that we can use transmission spectrum from JWST to potentially place constraints on the carbon to oxygen ratios in the atmosphere of KELT-24b, which is great because one of the other interesting questions for this planet is where could it have formed in the solar system? And by probing this type of a measurement, we might have an idea or might be clued in further to where in this disk KELT-24b may have originally formed. So in the puzzle that is this KELT-24 planetary system, a lot of the pieces have now kind of been able to be filled in, but there's still a handful that we just don't know. And so more efforts are going to be needed to follow up on the system to learn more about not only the star, not only the planet, but also what this background or bound source, KELT-24b, BC, BCD maybe, we don't know how many things there are underneath that, what these all could be. And so more efforts will be needed on the star. In general, though, KELT-24b is a really well-lined hot Jupiter. It's really dense. It's an excellent candidate for atmospheric follow-up, and some high-resolution adaptive optics imaging may even help to disentangle the really curious architecture of this system where we have maybe an eclipsing binary and a transiting hot Jupiter system that are orbiting in a strange way, perhaps. But then some open questions still that need to be addressed. It's worth reminding everybody that our adoption here is for the case where we exclude the broadband photometry from the SAD, sort of as just an unsatisfying answer to this question of what is the ultimate source of discrepancy that was found between the two independent discoveries from Rodriguez et al. And Horth et al. We just find that the most likely cause or the most probable cause, kind of in a proof by contradiction way, has to be the SED, we believe, but we do publish the results of all three to sort of leave it open to the reader to interpret what they would maybe like to consider for their analysis. KELT-24b's near circular orbit, we did talk about how the extra radial velocities help to bring that number closer to zero, suggesting that it could actually be on a circular orbit. But this is, again, an open question in terms of the planetary formation and evolution history for the system. And then more data, while it did help some things, it also opened up some new questions as well. So the problem is certainly not solved. And KELT-24b, we believe, really should serve as a blueprint for how we want to model our exoplanet and stellar systems moving forward, because these systems are a lot more complicated than we thought they were. And as a community, we believe that gone are the days of just finding a few transits, going after with RVs, putting in your statistics and writing it up, we're kind of past that. We have to be careful about how we're modeling our stars. We have to compare how our models fit for parameters like stellar density using the transits and SEDs, and do a bunch of internal comparison checks. And so more dedicated efforts to this type of modeling is needed. So I'm going to leave these conclusions up as I take some questions, and I'll thank you all again for your time.
Awesome. Thanks so much, Mark. Does anyone have a question? Joe? Oh, okay. Yeah. If you want to ask a question online, please go ahead.
Yes, hi. This is a very interesting talk. I'm just wondering, you sort of zoomed into the SED as being your problem. The SED is a problem, and you have these three methods. There should be some way that you can simulate a situation so that these three methods give consistent results, and that would pinpoint, the problem.
That's a good point. So
simulated data, just simulate them so that they agree. Then you'll see what's missing or what's wrong.
That's a very good point. Yeah, the idea is, could we simulate some sort of, I guess, an architecture similar to what we're observing here in KELT-24 to determine what could be the source of the problem? I think the main problem in that is that what could be corrupting the SED is this background source. We do publish a best fit solution to this 3-star fit, believing that is the best result. But the problem is that there are far too many degeneracies, even when fixing the hot Jupiter to just sort of exist based on one of the best fit solutions. There are too many degeneracies by trying to solve for what the source of the corruption in the SED could be. And so we sort of leave that as an open question.
Yeah. That's usually the problem, the degeneracies. But if at least you can show that, if there's 2-3 cases where if that is the issue, then they agree. I think this is major. Of course, the degeneracies you can't do much about,
Yeah, that's a good point. Ideally, we would be able to simulate that, but you're right. The degeneracies are sort of the wall we run into here with being able to isolate the SED, certainly as the source of the problem here.
Great talk. Hello? Oh, there we go. If the SED is one of the issues, potentially, could you do follow-up observations with adaptive optics very similar to what the NERC2 data were, but there is visible light adaptive optics, for instance, at using like MAG-AOX on Magellan. Is that a possibility?
It is definitely a good point. Yeah, so the question of can we just go after the system with additional high-resolution adaptive optics imaging and try and get maybe a better sense of what this balance source could be? That is definitely the next step here to go after. It sort of became, I think, at that point, a little bit beyond the scope of what we had. Originally, this was going to be a simple, let's just reanalyze the system, let's add some more data, let's figure it out. And then we unboxed this whole thing of all these stars and planets. But so the next step here really is to go after high-res AO imaging targeted at that source to see, one, if we could get further evidence that is not well modeled as a single star. If we do see, depending on the structure we see in the photometry from that future AO imaging, we may be able to get better insight as to what could actually be going underneath and whether it's 2 stars, whether it's possibly 3 stars, what's going on. So that is certainly the next step.
Yeah, great. Hear me or no? Yeah? Okay, great talk. Very interesting system. This question of undiscovered binaries and their contribution to the formation history of the planets is a really interesting question. You have a weird planet around a weird star, active star, unusually active, with now a possibly triple, hierarchical triple structure. Have people started to look at any of these other high-density Jupiter systems to see if binarity or, their order could be somehow contributing to the formation of your planets?
That's a good question. I don't know anything about the, I guess, the correlation that exists between some of these dense hot Jupiters and the hierarchical stars that, maybe orbit those stars too. But I think that would be worth looking into, take some sample of our dense hot Jupiters and maybe get an idea for what's happening with their stars and if there are other stars orbiting those that are co-moving. Yeah, no,
you only really discover these once you actually do high contrast imaging of the systems, which is for a otherwise normal transiting, there's millions, right? There's tons of these transiting systems. But now if you have a very small subset of these high density hot Jupiters, maybe going and doing some, high contrast survey, interesting.
It definitely would. Yeah, I guess it plays into the last question too, where that is certainly the next low-hanging fruit here. What to do would be to target that these 2 stars with higher resolution adaptive optics imaging to get a better feel for what could be going on here, and then maybe branching out and comparing that to the landscape of similar-looking systems.
I'll ask a question. So not to harp on the AO stuff, but so earlier on you showed this sort of analysis that you did of the kind of allowed periods for that previously presumed background object. Do the KELT-24 images constrain that at all, or did you look into that?
Like the original KELT photometry, you mean, or the?
Well, yeah, so like that sort of plot of allowed periods based on the test sectors and that one transit that you have, or that one eclipsing event that you have for that secondary that you resolved in that KELT-24 imaging. Can the fact that you're still not resolving two stars for that secondary thing, does that constrain the allowed periods at all?
I see. Yeah. So right, we can't the contrast limits. I don't have them in the plot here. The contrast limits that we were able to place on that background source are basically that those things could still be separated. For instance, I guess to provide some perspective to that system, while they're 2 arcseconds away, they're about 200 AU away. And so, anything within probably, I'm sort of making a guess based on some of the contrast limits that I remember we got, but I mean, these stars could be, 10 AU away or so from each other, and we were only able to rule out a few years of anything beyond 3 years that we could not rule out as like a possible time that could be orbiting, and so it's way too small just based on the baseline of tests that the likelihood that those two stars would be orbiting in a much higher period, a few years or 10 years, is a lot greater than like the period space we're able to actually rule out. So the fact that we could only rule out anything below 3 years from the test baseline sort of excludes any possibility that we could place limits on that from the AO imaging that we have, which is limited.
Great, thank you. More question?
Hi, nice talk. I'm Shubhajit. So, any of those components shows any activity, like stellar activity, apart from what you are doing, like flares or any other thing?
I see. So between KELT-24 and the bound source too. So one problem we have is that much like a lot of the photometry, is that our spectroscopy is also a blend of both of these stars, which complicates things further because they're so close. Now, in the region that our spectrometers are going after this, it's not quite into the infrared just yet, and so the relative brightness between those two is mostly faint. So we don't believe that KELT-24b is a major source of blending in the spectroscopy that we have. But in terms of the activity of the KELT-24, we know that it's really active. It has a rotation period of about 3 or 4 days. But we don't see that necessarily as a signature in our radial velocities, as evidenced by that periodogram that we have. So beyond the fact of just saying this is a very active star, we don't do a ton of analysis into what the stellar activity could actually be.
Awesome. Well, let's thank Mark.